This is video number 7 for the assembly programming and reverse engineering course. And in this video I will talk about Windows API calls, the Microsoft 64-bit calling convention, and about stack alignment. And I will split this calling convention topic into several video parts. This is the official link from Microsoft to the documentation. But this documentation can be pretty confusing. So therefore I hope after watching these videos this topic will be easier to understand. So the 64-bit calling convention is a standard ABI, and that stands for Application Binary Interface, used on 64-bit Windows. The convention defines how parameters must be passed to functions, how the stack needs to be aligned, how functions return values, and which register must be preserved. For our own functions, we can deviate from the convention, but best practice is to stick to the convention when making calls to something like the Windows API or the MSVCRT, so the Microsoft Visual C++ Runtime Library. It's essential to stick to the calling convention, otherwise the software will malfunction. So whenever we call any Windows API function, then we need to stick to the calling convention, otherwise that will lead to a lot of problems if we don't stick to the convention. Stack alignment before calling Windows API function, the stack needs to be 16-byte aligned, and I will also explain in this video what all that means. Additionally, it's also required to reserve 32 bytes of shadow space. If a function has more than 4 parameters, additional parameters are passed on the stack. Each stack argument occupies 8 bytes. Why the stack alignment is needed? There are instructions that expect 16-byte alignment, especially the SIMD instructions. Stack alignment also helps the CPU to run the code safely and efficiently. Parameter passing via registers, integer valued arguments, are passed in RCX, RDX, R8, and R9, and the remaining parameters are passed on the stack. And in this video we will focus on the integer valued arguments. What is considered as integer arguments? Everything that is not a floating point value. Some Windows API functions expect float or double parameters, for example GDI+, direct 2D, direct 3D, direct XMass, and so on. And we will focus on this one, on example 1 in this video. Okay, so func1, this is just any function, that's just a function signature in C. And here are the parameters A, B, C, D, E, F, and int. That stands for integer. So the first parameter, A, goes to RCX, B goes into the RDX register, C goes into R8, D goes into R9, and the F register is then passed on the stack. This is the first code example. I've talked about most of this here already in video number 5, so I will not do it again. Only this one will be new, the section BSS and the BSS section that is used for uninitialized data. The first variable here, the name of the variable is bytes written, RASD, that means reserved dword. It's 1, that means that we want to reserve 1 dword, and 1 dword has a size of 32-bit or 4 byte. If you don't know what dword is, then just go to the MSDN, type MSDN Windows Data Types, and then look for dword, and here we can see a 32-bit unsigned integer. So that is a dword, and we pass this variable to the write file function, and then later the write file function will write data into this variable, and it will write how much data or characters we have printed on the screen. So this then later will hold the value 6, y6. Here's the string 1, 2, 3, 4, 5 characters plus the null terminator, so in total 6. Okay, then I will talk about the Windows API functions at first, and then I will talk about the stack alignment. So the first function that we're going to call is this one, get std handle, and this function returns a handle to the console output buffer, and we need to use this handle to so that we can then later print text on the screen. And the handle, that is something like it's something that allows us to access specific resources of the operating system. So for example, if you want to access files, input or output devices, network sockets, registry keys, and all of that, then we need to use a handle. And there are different handles, and in this case we want to have access to the output handle, so we need to pass this value -11. We move it to the ECX register in the Windows calling convention from the MSDN. We have already seen that the first parameter is RCX, but in this case we use ECX because get std handle that expects a D word. And we can also take a look into the documentation. So here's the explanation for the function. Retrieves the handle to the specified standard device, standard input, standard output, or standard error, and we want to use this one, standard output. This is the function signature. It's written in C. And this is a return value. So this function returns a handle, and a handle is an 8-byte value, or 64-bit. And here's a function name, and this is a parameter, and we need to pass a D word to this function. Here's the explanation for all the parameters that we can pass to this function. And we want to use this one, std output handle, and it's a D word, and here's the value, -11. So instead of RCX, we use ECX because get std handle expects a D word. And when this function is successful, then it will, then we can find the returned handle in the rex register. Okay, the next function is write file. This might be now a little bit confusing because we don't want to write to a file. We want to write to the console output buffer, but we need to use this function. Okay, the first parameter is a handle, and then we pass the handle that we have got from getStd handle. Now we pass it to the RCX register, the first parameter of this write file function. And now why RCX and why not ECX? Because a handle is a 64-bit value, so rex is holding a 64-bit value. Then we move it to RCX. And the next one is a buffer. This is the variable that that is holding the value that we want to print on the screen. Then we use a lia instruction, load effective address, and then we load the address of the text variable into the RDX register. And the next one is this one. The parameter is also, so this is a D word. And you can already see number of bytes to write. So we need to tell the function how much characters we want to print on the screen. And we can, I've talked about this already in video number 5. So if we disassemble this program later, then we will see, then we will here just see the value 6. And since this is this parameter needs to be a D word, we move the data into R8D, not an R8, but an R8D. And I've talked about CPU registers. I think it was in video number 4. Okay, the next one is this one, LPD word, number of bytes written, and LPD word, that means this is a pointer, and a pointer on a 64-bit system has a size of 8-byte, so or 64-bit. And what is a pointer? The pointer is basically just address, like something like this. 1, 2, 3, 4, 5, 6, 7, 8. And that is a pointer, and this pointer is holding another address. Let's say this one, 8, 7, 6, 5, 4, 3, 2, 1. And on this address, we can find, for example, the string hello and the null terminator. And that is a pointer. So the pointer just tells us basically where we can find data in memory. Okay, the next one is this one, the structure, and we need to pass a keyword, so 64-bit value. In this case, we need to pass the value 0, y0. We can take a look at the MSDN. Okay, so this is a function signature. And yeah, here a bool that is true. So this function can only return true or false. True is 1 and false is 0. So when it's 1, then that means that the function call was successful, and when it's 0, then that means that the function call was not successful. Okay, so then we can talk about the last parameter. So this is this one that we overlapped. So you can see a pointer to an overlapped structure is required of the file if the h file parameter was opened with file flag overlapped. But yeah, we didn't do that, and therefore we can just pass the value null to this parameter. Then we can call the function. And the last one is this one, exit process. And exit process that expects also a 32-bit value, so therefore we will use the ECX register instead of the RCX register. Then I will now talk about the stack alignment. And if we want to align the stack, then RSP needs to be a multiple of 16. And if RSP modulo 16 is equal 0, then the stack is aligned. So that is important that we do that. So if you don't know what this modulo operator is doing, it's a modulo operator. It returns the rest of a division. For example, if we have something like this, 35 divided by 8, that is 4. So ignore everything after the comma. So 35 divided by 8 is 4. And then take this 4 times 8, that is 32. Then take this 35 minus 32, that is 3. And we can see that this 3, that is the rest of this division. If we have something like 4 divided by 2, so 4 divided by 2 is 2. 2 divided by 2 is 2 times 2, that is 4. And 4 minus 4, that is 0. So in this case, there would be no rest after this division. And now I will assemble the program, and I will use the script again. And then I will also program an x64 DBG. And here we can already see the RSP. So this is the address of the RSP. And the last value of this address is 8. So that means RSP modulo 16 or 10 in hex would be 8. If this would be 0, then RSP modulo 16 would be, the result would be 0. Now we'll use Windows calculator, and now we'll use the programmer mode. Click here on hex, enter the address, and this is the modulo operator in the programmer mode. So click this icon and then type the value 10, because 10 in hex, that is here 16 in decimal. Then click the equal symbol, and here we can see the result is 8. And if we would have a 0 at the end, then the result is 0. Okay. What we know already, so RSP modulo 16 in this case is 8. But if we want to align the stack, as I've written here, RSP modulo 16 needs to be 0, and then the stack is aligned. Okay, so to make it now a little bit easier, I will just type sub RSP 8, and here's 32. So if we want to align the stack, then we need at first to reduce the RSP by 8. Then the stack is aligned, but we still need to reserve enough memory for the Windows API functions. And the function that occupies the most memory, this is one, it's write file. So we need to reserve in this case enough data for this function. So the stack is now aligned. We have reserved already 8 bytes on the stack, and then we can reserve, or then we need to reserve another 32 byte, and in total we have then reserved 40 bytes. So this is 8. This occupies 8 bytes. This is 8 bytes. This one 8 bytes. This one. So each parameter occupies 8 bytes, and in total we have 5 parameters, and yeah, 5 times 8, that is 40. And yeah, that is basically how the stack alignment works. And then I will quickly go through the code. So you can see now the last value is 8, and now I will execute the first command, sub RSP 28, and all these values here are hex values. Okay, so now I click on this icon, and we can see now the stack is aligned, and we have also reserved enough memory for the Windows API functions. And yeah, now click on this button, step over, because we don't want to jump into the get std handle function. And yeah, pay attention to the rex register. And here we can see the handle that the function returns. And then we pass the handle to the first parameter of the write file function. And yeah, we can also double click on these addresses, and then we can jump to the address here in the hex dump. Or we can also just hold Control, press G, and then enter the address. That's also a way how we can jump to memory addresses. And here's the last parameter. And now we will execute the write file function. And here on the screen now we can see the string hello. And we also can take a look at this one. So we can see here is now the value 6. And then we have the exit process function, and it will just exit the process. This is the last code example, and at first don't write code like this, because this is just too complicated. It's confusing and it makes no sense. Yeah, it's just bad. But it's a good exercise to get a feeling for the stack alignment. So this program will also just print the text hello on the screen, and we will see now how the pop instruction works. So at first I will assemble the program. And then I will load it again into x64 DBG. And here we can see now we are in the program, and the stack is not aligned. After executing sub RSP, the stack will be aligned. Okay, so the stack is aligned. Now remove the value -11 into RCX. So this hex value, that is -11 in decimal. Now RCX is holding this value. Here you can see -11, and we use this value as a parameter for the get std handle function. The next instruction is add RSP. That will increase the RSP by 8. If we wouldn't increase the RSP by 8 at this point, then after executing push RCX, we would decrease the RSP by 8, and then the stack would not be aligned anymore. Okay, so now I will execute this instruction. You can see the stack is not aligned anymore. Now we execute push RCX, and that will align the stack again. And then we will just reset the value in RCX X or RCX RCX. That will just set the RCX value to 0, because then later in the program we will pop the value from the stack back into RCX, and yeah, it's just better for the visualization for this video if this is then holding the value 0. Okay, so RCX, now it's 0. Then I execute this function, and then we will jump into this block, and this jumps to this function get console buffer output handle. Now we're in the function, the stack is not aligned anymore, and now we pop the return address from the stack into the RBX register. Here is the RSP, here is the return address, and the return address, it's here. So if we leave this function, then we jump to this address. Now I will execute the pop instruction, and the pop instruction increases the RSP by 8. And we can see the RSP is now also aligned. Then we execute pop RCX, and the RSP is currently pointing to the value that we have pushed previously on stack. So from here we have pushed the parameter for so we have pushed the first parameter for get std handle on the stack. Now we pop it down from the stack into the RCX register, so RCX is now 0. Now I will execute this command, and RCX is holding the correct value. The next instruction is push RBX, and what this is going to do now, we can see RBX is holding the return address, and now we push the return address back on the stack. Push RBX, it will decrease the stack pointer by 8, and then we push the value on the stack, and then later we can use this to jump back or to jump out of the function, so we can then leave the function. And execute the instruction, and you can see that the RSP is now pointing to the return address. Then the next instruction, sub RSP20. Currently the stack is aligned, but after executing sub RSP20, or 20 in hex, so 20 is in hex, and in decimal that's 32. And after executing this command, the stack will still be aligned, because 32 is a multiply of 16. So that means 32 modulo 16 is 0. And I execute the command, and the stack is still aligned, and it was reduced by 32 bytes, or by 20 in hex. And then I execute, then I click the step over button to jump over the function. Well, it will execute the function, but it will not jump into the function, because that is not what we want to do now. And the function is executed, and now here we have executed this command sub RSP20, and now we need to execute this one at RSP20, because we want we need to point to the return address. After executing this one, then we will point, so the RSP will then point to the return address, and then with red we can leave the function. And here you can see, here we have the return address, and then I will execute the red instruction, and it will jump to this address, and it will also increase the RSP by 8. Okay, now we are here, and the stack is not aligned anymore. And now we need to align the stack again. So sub RSP8, it will align the stack. And now the stack is aligned. Then we jump into the print text function. Now we are here. And yeah, this is basically, we know that already from the previous example. We reserve 40 bytes or 28 in hex. And then we can just execute the code. Then we'll now release the function. And we can also take a look into the console. Oh, no, that was not correct. Here it is. There is a string. And the next function is one exit process. So yeah, we just release the function. And yeah, that's everything for this video. And the next video, then I will show how all that works with floating point values.